Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Iman bin Muhammad Rahim. Matrix number DE20004. Today we would like to present about the group assignment Industry of Power Systems, lecturing by Dr. Nur Akmal binti Jamal. We are from section 5, group number 3. So now I would like to introduce my group members, which is start from group leader Muhammad Fakhrul Akudin bin Muhammad Nasir, Muhammad Aden, followed by Muhammad Hafizuddin bin Cik Su, Karti anak lelaki Puspanatan, Muhammad Azmi bin A. Halim, and Richard Ego anak Repai. Okay, now we're going to the first part of introductions, which is project background. The electrical power system grid consists of a few subsystems before the power is delivered to the consumer. Industry was the biggest consumer that consumed power as used various types of loads. Then substations are part of electrical power system that transform from high voltage to the low voltage or perform several other important functions. And lastly, for design of the power plant, an engineer needs to obtain a complete visions of desired plant. Then we're going to the second part of introductions, which is technical problems. The facilities electrical distribution infrastructure, such as the power supplies that are used for higher degrees of continuous in power supply, where put restrictions on the availability of power. After that, the voltage drop is the major causes from the process operating during starting the motor. Then the load can be estimating through the utilization factor KU and diversity factor KS. After that, to determine the basic transformer parameter, primary and secondary voltage and operational frequency, the selections and sizing of transformer is needed. Then selecting also takes into considerations the winding connections, cooling techniques, power factor, mounting configurations, types and efficiency. And the last one for the cable size of cable 1 for serving division 1, and cable 2 servicing number 2, and the last one cable 3 for servicing division of 3. For the last part of introductions, which is we're going to project objective. The first objective to estimate the total connected load, maximum demand, utilization factor and diversity factor by using Microsoft Excel. Then to determine the transformer size and main cable size. After that, to design the process of industrial power network, practical proposed layout. And the last one, to identify the issues and the possible solution based on the environmental and sustainability concern. That's all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. Okay, first of all, my name is Muhammad Azmi bin Halim and my metric number is DE200-105. Okay, so for my part, I will explain about the block diagram of this project. Okay, so what we can see here, this is the picture of the block diagram. What we can conclude from the block diagram is, from the block diagram, the design of the desired layout of industrial electrical system consists of the transformer sizing, cable sizing, and the estimated total load that we calculated for each load. The calculation of the power demand using the utilization factor and the diversity factor. The cable sizing is calculated by calculate the cross-section area to have the exact size of the cable to be applied. The transformer sizing needs to be determined correctly in order to fulfill all applicable loading criteria because of the crucial function that transformers play in electrical distribution networks. If it's too small, it might cause problem with electrical distribution system and cause load from stop flowing. Okay, that's all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Fakhrul Akudin bin Muhammad Nasir. My metric number is CE210147 and I am from Group 5. So for this presentation, I will take part to explain about the cable sizing, the result and discussion on cable sizing, the weakness of proposed design, and also design issues. So throughout in designing our project, in terms of issues regarding sustainability and the environment, we have point out a few issues. So generally, our industry we propose is electric instant water heaters, which means that our industry consume large power to consume all the load that has been gathered to run the operation. So the main issues here, the first one is that could be the lighting, because lighting is one of the loads that consume a large amount of power which used in large capacities, mainly in the factory. So generally in the factory, we know that we are using a lot of lighting to easier the manufacturing process. So for the lighting issues, for example, the average power of one fluorescent lamp is 100 watt, which is it is impossible to provide 100% of 100 watt at full capacity, because we have to take an account of the losses, which is about 30 to 40 watts. And then the losses of the lamp will be resulting in increasing carbon dioxide, which affect the losses from lighting, which affect also the environment. And then second issues we have find is that heavy machines that use in the factory. We know also that the heavy duty machines also consume a large of power. So an average one heavy duty machine consume about 550 kilowatt to 300 kilowatt, depend on its needs in the operation. So generally the heavy duty machine will have losses in terms of heating elements, as it has been operated all the time during the manufacturing process. So the heating element in the machine also can affect the environment.
My name is Muhammad Hafizul Mcekso, DE200106, and I will explain for the load calculation. So from the given data, we insert the data in this table to calculate the load estimation, and we have three division, the division 1, division 2, division 3, and it has have T2, T3, T4, and T5 distribution transformers. So in T2 we have induction motor 1, induction motor 2, induction motor 3, and for T3 we have lamp load and heating and lighting. And for the distribution transformer 4, T4, we have induction motor 4, MCC1 and MCC2. So at division 3 we have 2 DT, T4 and T5. For T5 we have synchronous motor. So this is the data given, and to calculate the operating motor power kilowatt, we need to calculate by using formula 0.746 multiplied by F3, which is horsepower. So we get the value is 2898.40. So we use this formula to calculate. And for this K is efficiency multiplied by power factor. And to calculate KVA, we need to use power kilowatt divided by efficiency multiplied by power factor. So we have K here, so we need to divide power in kilowatt divided by K, so we get the value of KVA. And next, for the estimated power demand, this is the calculation by using based on three categories, which is active power, apparent power, and reactive power. The rated voltage given is in this table, and for the active power we already calculate the value. So to calculate the reactive power, we need to use this formula, which is square root of S square minus P square. So we get the value for the A here, and we get the value for the reactive power. And to calculate A, we need to use the formula, which is S divided by rated voltage. So 292.61 417.93 divided by 3.3, so we get the nilai, the ampere is 126.65. And for the KUKS, for utilization factor and diversity factor, we just need to assume. So for induction motor 1, we use utilization factor 0.85, induction motor 2 0.25, 0.85. For the lamp load 1, and heating and lightning 1, and for the induction motor 4 0.85, MCC1 0.85, and MCC2 0.25, and for the synchronous motor 0.85. So to get this apparent power demand max, we need to multiply the utilization factor with KVA. So we get the value for the apparent power demand, and this value we need to multiply by diversity factor, which is we assume the value here. So we get the value of apparent power demand, and we need to multiply again until we get the value here, which is 3158.64. So that's all for the calculation. Thank you.
Hi, Doctor. I'm Karthi Puspanathan with the matrix number of DE2001 and 01. So I'll be presenting the transformer sizing part. So these are the three divisions given. So this is the transformer 2, 3, 4, and 5. So each transformer will have its own load. So this is the operating load, this is the peak load. We choose the same value for this situation. And then this is the apparent power. So apparent power will plays the most important role, which is we need to multiply with the utilization factor for us to calculate to get the apparent power maximum demand. So 0.85 is for the continuous load, and 0.25 is for the standby load, and 1 is for the lighting and lamp loads. So that's the reason why we choose separately all different utilization factor. Then once we multiply apparent power with utilization factor, we'll get apparent power maximum demand, and then we need to multiply with diversity factor 1. So we'll get answer of these answers, and then need to multiply the second one for us to get this one, and then finally with the third one for us to get the maximum apparent power for the first transformer. This one is for second. For the third transformer, fourth and fifth transformer, we'll use this value for the next calculations. So this is the transformer sizing. So these are the calculated values from the previous Excel file. So with this value, you need to add another 65%, which will become under 65% of this apparent power for us to get the 65% of the transformer. So the transformer sizing will become 5212. So we couldn't find a transformer rating with 5212. So we need to choose a higher value, which is the rating will be 6300. So that's how we choose for the entire transformer. So the type of construction is oil field, because it is oil field is designed for overheating, so we'll not have a overheating issue, and this oil field is more efficient. So that's the reason why we have choose oil field. So I'll move to the next slide. So this is the table for the impedance selection. So for each transformer, we have choose a different impedance. So for the first one is 7.5, for the second transformer 6.5, 4, 6, and 5. That's how we choose the impedance for the transformer based on the impedance table. So I'll move to the next slide. So this is the voltage drop calculation, or this value is the 65% of the transformer calculation, and this is the chosen rated transformers, and then this is the input voltage in the transformer, and this is the calculated I rated current value. So this is the impedance I showed just now in the table form, and this is the short circuit current. How much short circuit current can the transformer last? That's the calculation. And the SCE is the maximum short circuit capacity that the transformer can last. And then the last table is voltage drop. I put it in the percentage. So for a transformer, the voltage drop should be less than 10%. So all the calculation we got is less than 10%. So this is the desired transformers calculations. So this is the calculation for the transformer 1. So the chosen input voltage is 11 kV. And then the apparent power is from the Excel file, which is 3158.94. The impedance is 7.5, which is from the impedance table. And 65% of the apparent power, as I said just now, this is the value. And the chosen transformer size is 6300 kVA. So we need to calculate the I rated for the transformer, which will be, we need to use the transformer size divided by Z3 times 11 kV. So the reason why Z3 is because this is a three phase. So that's the reason why we are using Z3. So we'll get an answer of 330.66 ampere. For the short circuit, we need to use the rated current divided by the impedance. So we'll get 4408.8 kVA. And then we need to find the maximum capacity the transformer can work under short circuit, which is Z3 times voltage input voltage, which is 11 kVA times with 4408.86. We'll get 84,000 kVA. And then the inrush current we times 2. So we need to use the value of 3158, the initial apparent power. So we'll get 6,317.88 kVA. And then we need to use this inrush current divided by the short circuit current, short circuit apparent power, and then multiply with 100. So we get a voltage drop. So we get a voltage drop of 7.52%, which is less than 10%. So this is the ideal transformer. So thank you, doctor. That's all from me.
So for the cable sizing, generally we have three methods for determining the size of cable. The first method is short circuit carrying capacity, second continuous current carrying capacity, and last is starting and running voltage drops in cable. So for this design, we are using first method and second method only. So for the first method, which is short circuit carrying capacity, we have a few steps, which the first one, we have to find the apparent power in the short circuit condition by using total load, by using the formula short circuit is equal to 150 times total load. So 150 was assumed to be the short circuit capacity. Second, determine the short circuit current. The third is fault clearing time for each cable was different as the breaker operating time for each cable were different. So for the fault clearing time is different as we set for each the breaker operating time of each division is different. Third is to find the constant K by using the formula given. And lastly, we have to determine the cross-sectional area to determine the cross-sectional area of the cable. Second method is we use the continuous current carrying capacity. In the second method also we have to find we have a few steps, which is the explanation was given as the purpose of the second criteria was applied so that the cross-sectional area of the cable can carry the required current continuously at the design ambient temperature and laying condition. For the second method, we have four types of K, which is the K1 is stand for variation in ambient air temperature for cables laid in air or ground temperature or cables laid underground. K2 stand for cable laying arrangement. Third, K3 stand for depth of laying for cable laid direct in the ground. 4 is variation in thermal resistivity of soil. So the first step on the second method, which is we have to find the load current. After that, we have to find the constant K. So for the second method, it's easier because to find the constant K, we only have to multiply all the constant K1, K2, K3, and K4 to get the constant. And the third is we have to find the ICCC. So ICCC is stand for the continuous current carrying capacity, which is we have to times the constant K we get in the second step times by ampacity. So ampacity we have to refer to the table given by the manufacturer to get the value of the ampacity. So from that we get the value of ICCC. Next is the result and discussion on cable sizing. So the condition was assumed to be a 3-core aluminum XLPE. The 3-notch cable was laid 150 cm underground in horizontal formation with 45 cm spacing with 45 degrees Celsius ground temperature, and given the thermal resistivity is 150 degrees Celsius, and the short circuit SCC was given as 150 times the load, and given also the distance between the load and the source is 1 kilometer, and also for the fault clearing time is for the cable 1 is 0.24 second, for cable 2 0.14 second, and cable 3 given as a 0.24 second. So for the short circuit carrying capacity, we have determined the total load kVA from the load estimation demand, and then the voltage source for each cable is different as we have to refer to the design we have in the design layout. And then we have I short circuit. So the I short circuit is we have determined in the first method. Okay, so this is the result for each division where we find the cross-sectional area. So this is the result we have find here, which division 1 give the standard cable size 120, division 2 we have 300, division 3 for transformer 4 we have 70, division 3 for transformer 5 we have 120. So for the second method, which continuous current carrying capacity, we have followed the step in determined for the second method, and this is the result we have get here ICCC, which division 1 give the reading 105 ampere, division 2 163.02, division 3 for cable 3 under transformer 4 is 77.28, and for the transformer 5 we have 104. So from the ICCC we have to compare to the load current, which division 1, division 2, and division 3 give the result ICCC is less than load load. So it means that the cable size for division 1, division 2, and division 3 for transformer 5 is not safe to use as the load is more than ICCC. Only cable 3 under transformer 4 is safe for use. So for the conclusion, we can conclude that we have to propose another cable size for division 2, division 1, and division 3 for transformer 5.
Hello, my name is Vichik Gunarpai, DE200117. So I'm going to explain to you the industrial power network design that we proposed in our assignment. So firstly, you can see over here, this is the proposed layout design by our group, which over here, we're going to have the 3 division, where each division we're going to have its own transformer, which is T2 for division 1. And for division 2, we have T3. And in division 3, we're going to install 2 transformer, which are T4 and T5. Okay, so this is the proposed design for another 2 divisions with the total load of increment of 60%, with also considering the environmental and also the sustainability. So as for first division, we're going to install it with wind turbine as the main source, and for the another division, we're going to install the solar panels as its main source,
where we consider the environmental factors. So here I'm going to explain to you the sustainability and the environmental factors. So firstly, one division will be connect to the original source, which is on-grid wind turbine, and one more, we're going to install solar panel source for the off-grid. So smaller size wind turbine is installed in the roadside, as small size fan only needs small amount of wind to rotate and also produce electricity. And PV panel installation will help to reduce greenhouse gas emissions and lessening climate change. So these are the sustainability and environmental factors that we consider in our proposed layout for the network industrial design. Thank you.
In conclusion, right, after doing this project assignment, we rightly understand of both its theoretical and practical aspect. Next, we can determine proper distribution transformers and cable sizing for industrial power system. Thus, we are able to design and analyze industrial power system with energy resilience consideration for specific loading, such as using induction and synchronous motor. Okay, so lastly, you are able to design the industrial electrical system taking sustainability and the environment into consideration.
So for the weakness of proposed design, we also have determined a few weakness on our design, which we have identified. Um, so on top of that, the project may improvise by considering sustainability, which is propose a renewable energy as the main source. So for example, solar panels, which we have to propose the solar panel to replace the transformer to supply power to the load as part of the sustainability, and also to respond to an exclamation of the government, which aims to achieve net zero carbon emissions by 2050. So in addition, the software such as ETAP stands for Electrical Transient Analysis Program should be used as it's one of the most comprehensive analysis platform in designing, simulation and operation. For example, it can be used to analyze the fault that occurs in the proposed design so that engineers will take into account the precaution measures during the project installation at the site. So that's all from me. Thank you.